Okay. Can you hear me? Does it amplify? All right. It's 10:06, just to. All right. So I'm very pleased here to be here, participating in this celebration of Philippe's anniversary, and hopefully we will have another occasions of this kind in the future. This talk will be very different from the previous one in that there will be no applications. This will be pure mathematics, not even physics. It's a joint work. It's a joint Russian-Ukrainian project with Pasha Pulavsky. These are streetcars from our hometowns taking divergent paths. And the subject is linear incidence geometry. Linear incidence geometry is a classical subject. By classical, I mean at least 2,000 years. And the kind of results that linear incidence geometry studies are theorems of the kind that you see on the screen, where there are lots of lines, for example, here, and some of them intersect at a point. The theorem says that if you know about all these incidences and maybe you don't know that these three lines intersect at a point, then that condition will follow from the rest. Okay? So there is a theorem here associated with this picture, again, that says that if all conditions are given, one condition is removed, that condition is actually implied by the remaining conditions. Okay? Even though that, there is no apparent reason why it should. So historically, the first result of this kind goes back to year 340, Common Era, Pappus of Alexandria. You take any two lines in the projective plane, you pick 3 points on one line, pick 3 points on the other line, you connect them the way shown here, and then these 3 points of intersection lie on a line. Okay, magic. The first time you discover it, it should be amazing. And of course, nowadays there are computer programs that enable you to do this automatically and then move your points, and you will see that those 3 points will still lie on a line. And so you can marvel at it. Okay, so Pappus did it in 340. Maybe it wasn't actually discovered by him, but he was the one who recorded it. The next, historically, next theorem is much more recent. It's from 1639. It's a theorem of Desargues from Lyon. And again, most of you have seen it before. You have two triangles, red and blue. They're perspective from the same point. That is, when I look from here, the vertices of the red triangle block the view of the vertices of the blue triangle. And then if you extend the sides of each of the triangles, take corresponding sides, they intersect somewhere, those 3 points of intersection will lie on a line. That's the statement of the theorem of Desargues. In 3 dimensions, there are similar formulas, maybe less known. So the most famous theorem of 3-dimensional linear incidence geometry is due to Möbius. So unlike Pappus and Desargues, we actually know how this guy looked, and you can see it here. And the statement is, okay, so this was supposed to be colored, but somehow the rendition, so I can see it on the colors on the screen here, but the projector doesn't represent them well. So you'll have to bear with me. So take 6 points in the space. Think of these 6 points as vertices of an octahedron. Okay? The octahedron, as the name suggests, has 8 faces. So take those 8 triangles. Each of these triangles defines a plane. Those triangles, you can color them alternately black and white. Okay, so there are 4 black triangles, 4 white triangles. You take the 4 black planes, 4 planes generally don't intersect at a point, right? 3 planes in space will intersect at a point. 4 planes, if they intersect at a point, it's a miracle. So let's assume it happens with the 4 black planes. Then it happens with the 4 white planes. That's the content of the Möbius theorem. Beautiful theorem about points in 3 space. This is a projective theorem, just like the previous ones. No measurements are involved, no angles, no distances, no areas, just relative position, just incidences. Okay. And there are many such theorems, of course, in dimension 2, dimension 3, higher dimensions. Many such theorems have been discovered over the years. In 19th century, in early 20th century, many books have been published containing dozens of these theorems. So this is, of course, a classical subject. Of course, at some point, you begin to wonder, people must have begun to wonder where all of this is coming from. Is there some kind of system behind these theorems? And what kind of other mathematics is this related to? So I will try to answer these questions. So the most surprising thing about this is that apparently this is new. So apparently these questions that you see on the screen have been asked centuries ago and haven't been answered. This seemed like a cottage industry of some sort. You come up with a trick to prove this theorem, you come up with another trick to discover some other theorem, and then you compare them, it's kind of an art. I mean, it involves mathematics, it's rigorous, but there is no sort of systematic way of approaching the subject, apparently, until now. So the 19th century was the golden age of projective geometry, and these are some of the heroes. Jean-Victor Poncelet, famously, while sitting in a Russian prison, discovered many of the Poncelet porisms and related geometric results. Michel Schall, of course, contributed a lot. Jakob Steiner and Carl von Staudt, who developed a theory of algebraic approach to projective geometry. So this is the very first sentence from the famous Erlangen program by Felix Klein, who hailed the development of projective geometry as the most important development in the last 50 years in the field of geometry. And here is, if Klein is not enough of an authority for you, then here is Hilbert, who said that in 1932, since the 19th century, projective geometry occupied central position in geometric research, and theorems relating to incidence are by far the most important theorems in projective geometry. Of course, he meant more general results, like not just linear subvarieties and maybe Schubert calculus and stuff like that, but in particular, of course, the results of the kind that you just saw. Of course, every golden age comes to an end, and already in 1972, Paul Dirac, who was a big fan of, I guess in this audience I don't have to explain who Paul Dirac was a big fan of projective geometry, and well, you can read the quotation. So, all the elementary results were worked out, incorporated in textbooks. There wasn't any new work for mathematicians to do. So, you cannot publish papers, you cannot get hired for new results, so the field dies out, kind of. Yes?
I think the third name of Dirac is wrong. M.
Maurice. Oh, okay. Oh, great catch. Thank you. All right, my bad. I hope this will be the only mistake in my talk. Here is perhaps a better quotation still This one is from Bob McPherson and Mark McConnell, 1988. Classical projective geometry was, notice past tense, a beautiful field of mathematics. It died, in our opinion, not because it ran out of theorems to prove, but because it lacked organizing principles by which to select theorems that were important. And it was, again, isolated from the rest of mathematics. So, indeed it was, but I will try to convince you that it is no more. So, another nail in the coffin was put in by Monyov's universality theorem. Some of you know about it, and I guess it was even mentioned in one of the talks, which suggested that there is no reasonable classification of incidence theorems, because that would amount to being able to recognize which matroids are realizable and which are not. And Peter Shor, based on Monyov's theorem, proved that realizability is NP-hard. So this suggests that maybe there is no point in trying, and many people interpreted it exactly in that way. So, you know, the book is closed somehow. Like there is no reasonable classification. So all these questions just have no good answer, and we should pack and go home. On the bright side, the development of efficient commutative algebra packages based on Grobner basis technology provided efficient automated proofs of all such theorems. So if I bring you on a silver platter a theorem like Pappus or Desargues or something more complicated, you can just input that theorem into an existing software, and that software will spin its wheels, and in a few milliseconds you will get back a formal proof of that theorem, or maybe a disproof if it's not true, and the proof will be even human readable. It will be in the form of you know, checking that certain polynomial belongs to some ideal, and it will just be some algebraic identity which you can quickly check. And this doesn't seem to contradict what I told you before, because, of course, it's a certificate, right? So in this NP-hard business, you know, it's hard to come up with a certificate, but once it is given, it's polynomially checkable. So, you know, so it's so that's the situation. But of course, where did I get that theorem to bring you on a silver platter?
What do you mean by efficient?
Yeah, excellent question. So Grobner basis algorithms, strictly speaking, are not efficient, right? It's just like simplex method, you know? Like everybody uses it and it works just fine, even though there are counterexamples where it takes exponential time, or Ford-Falkerson, or what have you. I mean, efficient in practice, I mean. Like in reality, like all the theorems that you can ever reasonably care about, which you can state on a page of a textbook, those kind of algorithms will handle very quickly, like in a blink of an eye. But yes, theoretically, of course, they are not polynomial complexity there, right? Okay, so you can read these books by Richter Gebert, Sturmfels, and Li and Wu, and there are many other papers and books treating the subject. This is a digression sort of from the main, yeah, go ahead.
Don't understand the connection between this slide and the previous one where you said there is something hard, NP hard problem, and now you say that.
Yeah, right. This is about okay. Okay, we will. Maybe this will take us astray from the main direction. I would be happy to discuss it, but that's not the main topic of. Yeah, but yeah. Sorry. I hope you. It's an important topic. I just only have 45 minutes, maybe even less. So yeah. Okay. So So the key question is, where are these theorems coming from, right? So the question we just were discussing is how to prove a theorem when I bring you one, right? And that's an interesting question, but we sort of know a lot about it. But how to come up with a theorem, that's something which we know very little about. Which of these theorems are important and why? Of course, this is a matter of subjective opinion. And what kind of other mathematics are they related to? So our way of answering these questions is via some sort of a master theorem, which we hope encapsulates or includes as its special cases all the theorems that anybody here or somewhere else is ever going to care about. Okay, we're not saying every theorem that exists, but we're saying like all the theorems that we could find in the textbooks or that ever came, all the reasonable theorems. That's our belief. It's not a result. It's a mathematical statement, an imprecise one. Will be special cases of this.
I'm sorry, could you please bring the microphone move on the back while you were talking and bring it back to the front, please? Yeah. No?
No? This way?
Yes. Yeah. Sorry. Thank you.
Is it better?
Yeah, to record it.
Okay, thank you. All right. And as a result, we will obtain a unifying perspective on why these theorems hold. So I promised you a lot, so let me deliver now. So we will work with tilings of oriented surfaces by quadrilateral tiles. This is what Mireille called quadrangulations, right? So you start with a closed oriented Riemann surface, and we work in topological categories. So there is no geometry on the surface, just viewed up to homomorphisms. And we tile it with quadrilateral tiles. These are two examples. These are a bit simpler examples. These are two quadrangulations. Any such tiling endowed with a bipartite labeling of the vertices, meaning some vertices are black, some vertices are white, and every edge of the quadrangulation connects a black vertex to a white vertex, will give rise to an incidence theorem.
To a different one.
Again, to a different one, right. So again, there are two realms. In one realm, you have this surface with a quadrangulation, and this is just a blueprint. It tells you which lines to draw or which planes to draw and so forth, right? This is purely topological, combinatorial if you want. And then separately, there is a plane or space where your actual theorem lives, where you draw these lines, and when Pappus or Desargues or Möbius or whatever hold, okay? So these two separate domains. One domain is where we take that surface, we quadrangulate it, take any quadrangulation with bipartite coloring, and then based on that, we do the drawing, okay? So now the recipe. Okay, now let me be formal a little bit. So P is going to be finite dimensional projective space, let's say of the complex numbers. Then a tile is one of these tiles that our surface is going to be partitioned into. And to each black vertex, we are going to associate a point in our geometric space. And to each white vertex, we are going to associate a hyperplane. Okay? So again, quadrangulation, black and white points. Each black point here corresponds to a point in the geometric space. Each white point here stands for some line, or more generally, hyperplane in this geometric space. Okay? And we say that such a tile is coherent if, first of all, some soft conditions, like we don't want A and B to be incident to L and M. On the other hand, if A equals B or L equals M, then it is coherent. But generically, what is required is that this line, the line that passes through A and B, pierces the codimension 2 subspace, which is the intersection of L and M. So L and M intersect at something codimension 2, and something codimension 2 and a line generally miss each other. We don't want them to miss each other. Okay, that's a single equation. That's the coherence condition. Now, for example, in dimension 2, if you have such a tile, saying that it's coherent means that the line that passes through A and B and the point, which is the intersection of L and M, are actually collinear. Okay? It's the only sort of natural condition that you can impose on 2 points and 2 lines. Right? What can we say? 2 points, draw a line through them. 2 lines, take a point where they intersect. You want that point of intersection to lie on the line that we drew earlier. Okay? That's the coherence condition. Now the theorem comes. Master theorem. Start with a tiling. This is a tiling of a torus. Looks like a hexagon, but you're supposed to glue its opposite sides to each other, left to right, this to this, this to that. Then it closes up into a torus, right? So consider tiling of a closely oriented surface by quadrilateral tiles, vertices colored black and white, like I told you before. Associate points, respectively hyperplanes, to black, respectively white vertices, as I told you earlier. And I don't want any of these points to lie on any of these lines, or hyperplanes more generally. And then the theorem says that if all tiles with the exception of one are coherent, then the remaining tile is coherent. Okay? That's the theorem. That's it. Okay? Now, sketch of proof. It turns out that coherence of each tile is equivalent to a certain natural projective invariance, the mixed cross ratio of these 2 hyperplanes and 2 points. There is like only one thing, only one projective invariance that you can associate to this, and that's this mixed cross ratio. We require it to be equal to 1. It's easy to check that that identity, that this thing is equal to 1, is equivalent to coherence. Now, if you multiply all these cross ratios over all tiles, this will be a telescoping product. The product will be equal to 1, because each of these pairings will appear in the numerator for one tile and the denominator for the neighboring tile, because your surface is oriented, so when you look from inside the tile, depending on whether going clockwise you go from white to black or from black to white, it goes numerator, denominator, but when you look from the other side, you go from white to black, not from black to. And so the big product will be 1. Coherence means the product, the individual cross ratio is 1. So if all of them are equal to 1, with the exception of a single one, since you know the product of all of them is 1, it follows the remaining one is also 1. End of proof. So it's said that every talk should have a proof. In this case, it's a proof of the main theorem. Okay, so that's nice. Now, seems easy. Why wasn't it done before? Well, the hard part is not actually proving this. Of course, the hard part is discovering it. But even after you discovered it, the hard part is actually realizing or figuring out that classical theorems of incidence geometry actually are special cases of it. Like anything we were able to find, and this is a list of some results, is actually a special case. Let me show you in a couple of examples. This is Desargues. Okay, so this is our Desargues configuration. I strategically choose certain points, namely A, B, C, D, and certain lines, namely P, Q, R, S, and I place them at the vertices of the cube in this particular way. Now I claim that if you look at the coherence of these faces, then and then apply the master theorem, this will be exactly Desargues' theorem. For example, let's look at the front face of the cube. And of course, cube is a sphere, quadrangulated sphere, right? So AC and then SQ. So we need to take the line AC and the intersection of S and Q. Where is intersection of S and Q? S and Q intersect here. Line AC, wow, goes through that point. Or the left one, AD, RQ. R and Q intersect here at this point, and AD goes through that point. Okay? So you just check all these conditions are indeed satisfied there. If you remove one of them, this will be sort of the conclusion of the Desargues' theorem. You convince yourself that the master theorem just gives you Desargues. Okay? So it seems, okay, maybe it's tricky, but like how did I figure out which points and which lines to take and where to place them at the vertices of my quadrangulation? So it's tricky, but doable once you believe in the yoga, right? Okay, but even...
As you have this arbitrary choice of where to put numbers and where not to put them, maybe different surfaces give the same theorem.
Well, I mean...
Didn't you tell that there is a choice there?
Well, there are plenty of choices, but if you...
What to give a name to and what not to give a name is a choice.
Exactly. So you want to come up with a quadrangulation that will exactly encode the theorem at hand, and that's a highly non-trivial task, like figuring out which ones to give a name to, and like you said, and which one. Let me show you the Pappus theorem. It's even trickier. With the Pappus theorem, a simple-minded approach like you just saw doesn't work. In fact, what you need to do is to take these 3 points in the Pappus triangulation, and instead of taking those 3 points, take the 3 sides of the corresponding triangle. These will be lines PQR, and then put points A, B, C, D, E, F, and the lines PQR at the vertices of this tiling, this quadrangulation of a torus. Again, this is a torus. You are supposed to glue the opposite sides to each other, and then you will recover the Pappus theorem. So for example, this tile AFQR, okay, AFQR, Q and R intersect where? Q is that one, R is that one. They intersect here, and QR and who was? AF, and AF are this. It goes through that point. Magic. Okay? And you check that these 9 conditions for the 9 tiles of this quadrangulation exactly correspond to the 9 lines. Yes?
Sergey, I have a Dave question. So it would seem, according to this example, that you can attach a genus to the
Right.
theorem on the right.
That's right.
Is this a general fact?
Well, so it's a natural question, and indeed you are anticipating one of the problems that I will state very soon. Like to determine the genus of the theorem that corresponds to a given incidence, genus of the surface that would prove a given incidence theorem, we don't know how to do that. In fact, it doesn't seem to be an invariant of the theorem, and there could be non-isomorphic quadrangulations that prove the same theorem, but interpreted in different ways as instances of the master theorem. And even the same theorem, the same surface can have non-isomorphic quadrangulations that would give the same theorem. Eric?
Can you read off what the dimensions of projection space is?
Excellent question. So in fact, every quadrangulation gives us a sequence of theorems. In each dimension, there will be a theorem. And sometimes in small dimension, it's a trivial theorem. In large dimension, it's a non-trivial, and sometimes it's the other way around. And we don't have a general understanding of how it works. Philippe?
Yes. How do you know it's a non-empty theorem in the sense that there exists really a configuration?
I'm not saying I know it. So the way I'm approaching it, we know Pappus theorem, right? I sort of want to teach it to my class, and I just pull a rabbit out of the hat and I say, here is the quadrangulation. Don't ask me how I came up with it, right? And this is the proof of the theorem, right? But of course, remember, what was my goal? My goal was to come up with a secret way of coming up with new theorems, right? Right? So in the old days, I would have kept that a secret, and I would publish a new paper every month, which would come from I wouldn't tell anybody that they actually come from quadrangulations, right? It will be a theorem, and the proof I would get from some, Grobner basis of something, and it will be an ugly paper, but it will have a new theorem, right? Yes, go ahead.
Can one imagine to be able to do some sort of fusion, like take two theorems
Yes.
and make a third one?
This is coming. Excellent. So maybe I will move faster because Philippe already knows what I'm going to say. Okay, so this is, for example, the complete quadrilateral theorem, another famous result. I don't have time to explain what it is about, and this is the proof. It comes from this quadrangulation. Like all of this will be like that. Permutation theorem, this is another famous theorem, and the proof comes from this tiling of the torus. So again, like you don't have time to check any of this or even like absorb the statement of the theorem, but I can mail you the slides, or maybe they will be posted. It's also in our paper. You can go home and check that I'm not lying, or else sue me. Okay, so that's how it goes. Of course, we can come up with new theorems, right? Because you can just, like I just told you, start with a quadrangulation, and it gives you a theorem, right? So this is an example of a new theorem that we discovered. We call it the 2 stars of David theorem, because you can see there is like a red Magen-David and a blue one, and they are kind of mutually inscribed. So, and again, like you take one of these points, like we're triple intersection, imagine this is not given to you and everything else is given, then this will follow from the rest of the remaining incidences, right? Like how in the world could one even come up with a statement like this? Well, easy. You just take this tiling of a torus and then you just unpack it, like figure out what is it saying, what this instance of the master theorem is telling us, and you will get, it will just fall into, that theorem, that the 2 stars of David theorem is just a direct interpretation of the master theorem for this particular tiling. So it doesn't require any brain power. We already have all the technology. What about 3 dimensions? Möbius theorem, easy. Comes from this, okay, again, when I say easy, I mean it's easy to check. It takes some time to come up with a given quadrangulation. We don't have an algorithm for that. But once somebody found it, then it's easy to check that this gives indeed a proof. Here is a new theorem. I don't have time now, so we call it 13 lines theorem. It's a three-dimensional theorem about 5 lines piercing 2 lines, and then certain process closes up. So anyway, that's a new theorem which came from this quadrangulation of a genus 2 surface, just to show you something that comes from higher genus. So, which problems remain? Well, the first natural question is, can any theorem of linear incidence geometry in the real or complex projective plane be obtained as a special case, right? We don't know. There are some signal symptoms, reasons to believe that it's actually not true, that maybe there are some very complicated kind of pathological examples, but we weren't able to find any theorem that anybody ever cared about that is not a special case. And of course, remember, McPherson said, we need to figure out which theorems are important. So why not define important theorems? All right. Okay, problem 2. Is there an efficient algorithm for constructing a tiling that delivers a proof of a given incidence theorem, right? So we don't have such an algorithm. And of course, what's the minimal genus as, yes?
The answer to problem 2, no, because of the NP-hardness?
I don't know, like directly, again, yeah, this is Probably the answer is no, but right. Maybe the word strike, yeah, okay, depending on how you define efficient. All right, so now, since I'm behind schedule, let me just very quickly go through a bunch of slides. So there is an alternative setup where instead of starting with a quadrangulation, we start with a triangulation. And then given a triangulation, you can construct a quadrangulation by picking a point inside each triangle, like so, and connecting it, coloring this white and the point inside black, doing like this. Now the black stuff gives you quadrangulation, right? So this is a standard construction. And then there is some kind of master theorem for triangulations, which comes out of that machine, which you can imagine what it says, but let's skip it. So in particular, so it involves like placing points on the sides of the triangulation, not just on the vertices. And I explain here how Pappus and Desargues can also be obtained from that approach. And that in fact we can also go back from the triangulation version to the quadrangulation version. Okay, again, don't have time to explain. But remember, the one thing that you need to remember from one of the slides that I flashed at you, this one, is that Desargues corresponds to a tetrahedron, like the simplest triangulation of a surface there can be. Just triangulation of a sphere by 4 triangles. That's Desargues. And Pappus, again, is some kind of triangulation of a torus, just like before. Desargues was a sphere, Pappus a torus.
Question.
So,
Is that the simplest possible result on the sphere?
yes,
Start
yes,
the other ones.
yes,
Trivial.
right, correct. So these flips can be viewed as gluing in a tetrahedron, right? These are like, we pass from one triangulation to another using these things. This corresponds to gluing in a tetrahedron, which can be interpreted by what I just told you as applying Desargues theorem. So, and it's easy, it's a classically known fact that any 2 triangulations of a given surface can be connected to each other by these transformations, which implies that any 2 incidence theorems that come from triangulations of the same surface are equivalent to each other modulo Desargues.
Only the genus remains.
Exactly. But even the genus can be handled because we can just apply Pappus. Remember, Pappus is a torus, and we can glue these tori to increase the genus by gluing a torus. And gluing it exactly corresponds to applying Pappus. Okay, I'm skipping details, but you can imagine. And so basically everything follows from Desargues and Pappus. And actually Desargues follows from Pappus. We can explain again, like you can glue tori to get a sphere. You can actually lower the genus as well. So let me skip that. And now let me just very briefly outline some connections to some other mathematics, right? Because that's also what I promised you at the beginning of my sales pitch. So instead of looking at quadrangulations, we can look at the dual object, which is multi-curves on the surface, right? For each tile, connect the opposite sides of the tile by a segment of a curve, and then connect them across those edges, and you will get several closed curves which intersect in a transversal way, right? So quadrangulations are cryptomorphic to multi-curves. It's just the same object, just in disguise. And for example, the Pappus theorem, the proof that I showed you earlier, comes from this particular now it's multi-curve on a torus. And the permutation theorem comes from this one. So so I could just recast my our master theorem as a theorem that starts with a multi-curve and then uses that as a blueprint for creating an incidence theorem.
Do the colors have any meaning? Is there any
These are connected components. I mean, like the closed, like immersed circles.
But you could have chosen every vertex to have the colors kind of avoid each other rather than cross each other. Would that make any difference?
Sorry, I don't understand.
You could think of osculating path instead of crossing path.
Oh, yeah. No, these have to be nodal curves. I mean, they have to intersect transversally because each such crossing in the dual picture corresponds to a quadrilateral tile.
No, I know. It's just a question of interpretation. Do the colors have any meaning? Like,
The only meaning they have is that these are immersed circles. When you any nodal multi-curve is a union of immersed circles.
So you give a different color to each circle.
To each circle. Yeah, this is just for ease of reading. I could have colored them all black for all purposes. Okay. Now remember, a flip and a tiling corresponds to Desargues. So not remember, sorry. A cube corresponds to Desargues, and a flip is like gluing in a cube, right? But in the language of these curves, flipping, this kind of flip becomes a Reidemeister move. And so when we talk about theorems equivalent modulo Desargues, these are multi-curves which are equivalent modulo these kind of moves. And there are also some simplification steps which kind of make your quadrangulation smaller. And so for a given closed-oriented surface, equivalence classes of nodal curves modulo these local moves correspond to equivalence classes of incidence theorems modulo Desargues.
Is the simplification true or the right?
Yes.
Right.
Yes.
Oh, yeah.
Yes.
Okay.
Yes. I know exactly. It's good. It's precisely the correct reaction.
It's weird that it's this way.
It's weird, but that's what it is. Okay? And it can be proved using techniques that Rick Kenyon mentioned in his talk, that the reduction of a given multi-curve, when you simplify it, will be unique modulo Desargues. Yes. Okay. Well, let me just briefly mention another. I started at 06, so I still have several minutes.
No.
Yes,
No.
I started
No,
at.
you have 2
I-
minutes.
I even
Considering
mentioned.
the fact that there may be extra questions, that means
Okay.
0 minutes.
Well, you are the boss, so I have to obey. So there was this. So Desargues' theorem can also be interpreted as building some kind of 3-dimensional dynamics, where 7 objects define the 8th, and a natural question, according to the yoga of Babienko and Souris, that interpret discrete integrability as 4D consistencies, to ask whether this thing exhibits 4D consistency, and we prove that it does. And I don't have time to explain what that means, except to show you the picture. This is the incidence theorem that corresponds to this 4D consistency condition. Of course, nobody in his right mind would have come up with this theorem, but given the previous slide, you know where it comes from. And it can be reformulated as saying that Desargues flips satisfies the Malotchikos tetrahedron equation. So when you do these flips inside hexagons, and after 8 flips you come back, there is no monodromy. It's the same configuration on the plane. And so let me recap. The master theorem helps explain in a conceptual way why Pappus' theorem is more powerful than Desargues, why these 2 theorems imply all other theorems, why Desargues holds over non-commutative skew fields, whereas Pappus does not. I can explain this later. How to construct generalizations of existing incidence theorems, and also which incidence theorems can be formulated as Schließungssatze, like you do some construction, and then magically you come back to the same point. where you started, and this actually is related directly to the Hamiltonian paths that appeared in Philippe Bian's talk. You have a triangulation, and in the dual graph, if you have a Hamiltonian path, that path gives you this Schließungssatz. And many other things, and of course these techniques can be used to study many other things. The pentagram maps, skewers of Tabachnikov, configurations of circles and lines in the Möbius plane, theorems for higher degree, algebraic curves, theorems involving tangency conditions, closure phenomena, surfaces, fields of finite characteristic. I already mentioned uncommutative skew fields. You can extend it to elliptic hyperbolic geometry, so forth. This is just the starting of a big program, which you can imagine will take years to complete, but it's clear that we have the seed of this idea. And that's it. Congratulations.
Okay, maybe some urgent question, and or please.
So do I get it right that there's literally one important theorem in projective geometry now, the Pappus theorem? or over non-commutative fields, well, two, right? Well,
no, I mean, everything can be deduced from it. It's just a question what it means to deduce, right? I mean, in some sense, it's like saying, any theorem follows from Zermelo-Fraenkel axioms. I mean, no, but there is something to it. Like it's how it follows. That's what is important. How difficult it is to deduce. Like the genus thing tells you how complicated it is, right? So, but in principle, yes. Right. People knew it already before through the coordinatization result using von Staudt. Yes?
So your master theorem only holds for orientable surfaces?
Yes.
What goes wrong for the non-orientable?
Because you don't know for each cross ratio which way to go. Who goes into numerator, who goes into denominator. You need orientation to do that. And then there wouldn't be telescoping cancellation in the absence of it.
Okay, please.
Well, this is probably a stupid question, but you deal only with points and hyperplanes.
Yes.
That means there is nothing corresponding to incidence theorems for different dimensions of on one side and the other side?
We have a version of the master theorem where we place like objects of dimension k and codimension k, and there is a similar argument, and so. But of course, you can ask about flags and so forth, and we didn't do that. But I'm sure that there is a version of this theory for that.
Okay, please.
Yes. So you mentioned the connection between Pappus and commutativity.
Yes.
And as far as I remember from my old days, there is a connection between Desargues and associativity. And can you see that in your scheme, or if you have a projective plane and which satisfies the Desargues theorem, then you can put an associative ring structure on the lines. So
yes, I know what you right. I guess, yeah, the projective planes and spaces that we look at are not like abstract projective geometry in the sense of like block design theory, but they are like actually coordinatizable, because otherwise this technology doesn't work. So, yeah.
Okay, so let's thank the speaker again.